about what time zone people are in. If you guys want to tell me, you can tell me in the chat. You don't have to tell me personally, or you can send me an email. Either way, just let me know like what time zone you're in so that I can get a feeling for it. It'll make it, helps me kind of know like where people are at, like physically, as well as like where you're trying to log in from. Also, when we try to schedule like the assessments, like the quizzes and tests and stuff, then I'll have a better feeling for like where everybody is. We're going to try to be flexible about quizzes and tests. I'll talk about that in a minute. Let's just give it like one more minute for everybody else to come on. And if you guys want to, you can mute your audio, you know, when you first join, and you can unmute it if you have questions, if you want to ask them. You can think of this too as like a real lecture. It is going to be a real lecture. But don't be intimidated by the computer format. You are absolutely welcome to stop me during the lecture by saying, hey, I have a question. It's actually easier for me if you like turn off your audio and say, excuse me, professor, I have a question. Can you explain whatever, or can you, go back and do something? And if you put it into the chat, sometimes I won't see the chats because I'm focusing on like what I'm doing on the page, or I'm trying to answer questions and stuff too. So if you have things that you want to ask me, that you want me to answer right away, or that you just want to point out, feel free to, stop. Like think of this as like we're in a classroom, right? Where we're actually, interacting with each other. Okay. All right. Okay. So let's go ahead. I want to, kind of call your attention. This is pretty unique situation, right? We're all fairly new to the remote model. We all kind of got thrown into it last spring. And then I taught a course this summer that was completely remote, and it worked out pretty well. So I'm going to follow the same kind of format that I did this summer that seems to be fairly successful for my students for learning the material and doing things. If you have any questions or things, you're not quite sure where things are at, like on our course page, please just send me an email and then we can figure it out. Or you can talk to me in office hours too. I've got the office hour link on our syllabus, which happens Monday, Wednesday, Thursday from 1 o'clock to 2 o'clock.
Yeah. So am I.
I'm gonna mute that class right there. Okay. Anyway, so let's go ahead and I'm gonna just talk about the syllabus really briefly. This is posted on our main page for the home page for our class on Canvas, and it's also posted on our syllabus on our Canvas page as well. It's got like my name and my email contact. This is the department's phone number too, so you can always call and leave a message. I think email is probably our best way of contacting each other, or you can obviously come to my office hours, and ask me questions as well. So this is where my physical office is, but that's not obviously where I'm at right now. So like I say, email or questions in office hours, or questions at the beginning of lecture or throughout lecture are the best way. Let's see, office hours, here's our Zoom link, and then the passcode and the meeting IDs. I also have a YouTube channel where I'm going to try to post lecture videos for our lectures for each day. It sort of gives you an extra place to look at things in case you can't get to Canvas, and hopefully I won't max out of my space on YouTube. The course textbook, we actually have 2 textbooks for this class, but they're the same author, and I think you can get PDF versions of these here. They are Dave Massey's book, which is the first book, which is differential calculus, right? Which is our worldwide differential calculus, and then integral calculus, which we do like the first, basically like several sections of. And then you guys will be using that second book next semester when you take calculus 2. So it is worthwhile to get that book because you're going to be using it not just this semester, but you'll be using it next semester as well when you take Calc 2. Let's see what else. Yeah, so let's see, here's stuff about office hours. Like I said, I've got the office hours Zoom link posted at the top of the syllabus page, so you guys can get that. If you can't get into office hours or you're having trouble with that, shoot me an email. I'll check that out and see what we can do for that. So let's talk about what we can kind of expect. You can kind of see some of it on our Canvas page as well. Canvas is a new sort of web hosting program that Northeastern has shifted us all to. So this is my first semester using Canvas. So if you can't reach things or things aren't making sense on Canvas, please let me know, and then I'll contact IT, and then we'll see what we can do about that. So homework in the class, homework's really, really important for making sure that you get the material that we're covering each day. Homework is actually worth about 5% of your grade, so it's not like a lot, but it's enough to make you want to do it. It's enough to bump you up from like a B+ to an A-, say for example. what you're going to do each week that we have a quiz. So every Thursday, not this week, not tomorrow, but every Thursday we'll have a quiz on the material that we would have covered in that week's time frame, right? And the material on the quiz is going to be based on material from the homeworks, okay? Now in the past I've done verbatim homework questions, but that was when we were in person. But because we're now remote and you guys, all the assessments are assumed to be open book, open notes, I'm not going to do verbatim homework questions anymore, but I'm going to base the quizzes on homework problems. They'll be similar to it. So homework is really important to make sure that you get the material. So each week, by the end of the day on Thursday, you'll need to upload your homework, which you can upload in PDF. And I'll accept JPEG, but PDF is the best file format. So what you can do is I've uploaded the homework assignments. Let's see, there's a couple of things. So at the end of our syllabus here, it tells you like what chapter section we're on for that day and what homework problems. Now I went through our book and I said, okay, for question 3, 4, 8, 9, I copied those problems and I put them into a document. So the problems that I give to you as homework are these exact problems here that are suggested in our syllabus. So if you can't find the homework that's online for whatever reason, you've got like what the assignment is. So you can get it from the textbook. It's actually in the book. So what you'll want to do is download that homework onto, piece of paper. You don't have to if you don't want to, but you'll want to work through those problems, okay? And then either if you've got it on a piece of paper, which actually helps a lot, then you can take a picture of it, right, with your phone or scan it in or whatever, convert it or save it as a PDF and then upload the PDF to me, okay? And then each week what I'm going to do is I'm going to go through and I'm going to take a look at your homework. Now, what can you expect for the homework? So it's true that you're getting a grade on the homework, but here's how it works. So I'm grading for completion on the homework, okay? So if, say we have 10 problems on the homework, okay, it's typically we'll have more in each week, but if we have 10 problems on the homework and you've only done 8 of them, okay, you'll get an 8 out of 10, like an 80% on that homework, okay? Because I'm going to go through and I'm going to look to see, did you make a concerted effort to actually do the homework problems, okay? So this isn't about like, grading for correctness, because you guys are free to talk about homework problems at the beginning of each class. When we meet in person, typically we spend the first 10 minutes of each class actually going over sample homework problems, and I have students come to the board and people work it through and we talk about it. So we'll have to be creative this semester about how we want to go over homework in class, but I'm totally good with talking about homework problems at the beginning. We can talk about them in office hours. So the homework isn't some quiz that you guys need to get right and make sure you pass it in, okay? It's something that we're working through. We're trying to learn the material, okay? So I'm collecting it to make sure that you're actually doing this stuff. So if you're not quite getting what's happening as I'm working through the homework problems, right, then write it down. Write down what the solutions are. You'll have something to study from and to kind of think about, and you can ask me, we can go over like, how did this actually happen? What does it mean? So you get graded on your completion, right? So you get an 8 out of 10. So that goes into your grade book. It's not forever, okay? You will have a chance, right? I'm going to grade this stuff. I'll put the your homework on Blackboard. The old computer hosting program, I could do this on Blackboard and it would be up there. You could see it. We'll see how it goes here on this one. But on this, on Canvas, what you can do is if you have only completed part of your homework assignment, right, and you want to get more points back, like you've done 8 out of 10 problems, but you want to get like a 10 out of 10. So you go back over at some point and you finish those other 2 problems. You are free to resubmit your homework, okay? I suggest you resubmit it on Thursdays because that's when I'll be looking. And it helps if you send me an email, please check that I've actually resubmitted my homework, okay? Because otherwise I may not look for it, okay? This is where it's also easier when we're in person because people pass it into me and I have a physical copy. So you want to let me know to go look at the resubmission of your old homework, and then I'll look through and see that look at that you've completed the rest of the homework assignment. I'll change your grade from an 8 out of 10 to a 10 out of 10, okay? So conceivably, you could wait to the very last day of the semester and pass in all of your homeworks and get 10s out of 10s out of all of them. I would not recommend that, okay? That's like way more work for you. It's better if you keep up with it as you go. But don't look at this as an, oh, this is it. If I don't pass it in, I get a 0 or whatever. Yeah, you'll get a 0 for this week, but you can pass it in next week and then get a 10 out of 10, okay? So the homework is really about a place for you to learn, and there's flexibility, okay? I do want you to pass them in on Thursdays because one, we have our quizzes starting on Thursdays, And then 2, it gives me a chance to kind of look at things, you know, Thursday afternoon or Friday. Okay, so I can kind of get these, you know, grades in as we go. So it'll help you. Okay, but it's, you know, don't think of it as once you miss the boat on passing in a homework, then you're done. Okay, so so that's the homework, and you can ask me questions about this as we go along too, if you forget. But it's also in our syllabus. So the next thing about it is quizzes. Now, because we're remote this semester and we're kind of doing a lot of assessments, I've upped the percentage of the quizzes. The quizzes are now about 40% of your score, and there's a whole bunch of them. Like I wrote tentative dates and when we're going to have these quizzes. There's usually about like maybe 8 to 10 quizzes, and we do drop the 2 lowest quiz scores. Okay. We also don't let you guys do makeup quizzes, right? Because we're dropping the 2 lowest ones. So for whatever reason you missed a quiz, don't sweat it, you get a 0. That's the one I'm going to drop. Okay. But yeah, kind of keep that in mind as you're working on it. So 2 lowest quiz scores will be dropped. That's, you know, really nice, but it's 40% of your grade, which is, you know, quite a bit. But it just means like every week, starting next week, we're going to have quizzes on the material that we would have covered. Okay. And you can expect that, like, if we talk about new material on that Thursday, the new material will not be on the quiz that day. Okay. So it'll be stuff that we have had a chance to go over and talk about. So you're kind of familiar with it. You've gone over it. And if you've kept up with the homework, the quiz is going to look, you know, similar to the homework problems. Okay, so it's going to help keep you, you know, up on the material as we're going. Okay, so quizzes, you know, roughly. They have a question.
Yeah. So the quizzes, will they be available at a certain time every Thursday?
Yeah, that's a great question. So this is what I did this summer, and it seemed to work really well because people were all over the map in terms of time zones. And so what I did was. Let's see, so Thursdays, right? So I'll start the quiz availability window. I think I've said it right now at noon, but I'm flexible. I can start it at 4 o'clock in the afternoon if you want. And it will be available for 24 hours, okay? But it's a timed quiz, so you'll only have about, you know, 30 minutes to take the quiz. Okay, so once you start it, you gotta finish it, okay? But you'll have a 24-hour window within which you can work, okay? So like say you've got classes all day Thursday, you can't do it, maybe you're more awake, you know, Friday after lunch or whatever, and you want to take it because, you know, the window goes from 4 o'clock on Thursday to 4 o'clock on Friday. That's what I did this summer. We can talk about that if that 4 o'clock works okay, because depending on, that's why I want to know where people's time zones are, because then I'll know what availability window to set. So it's generally a 24-hour window for the quizzes. It'll be the same for the exam too, except that the exam, you'll have more time to complete it. So the quizzes are 30 minutes each, so it's timed. Once you start it, you got to finish it, but you'll have a 24-hour window within which you can do it. What also the department, our math department, has recommended is that we give 15 to 20 minutes for you on top of the assessment time for you to, after you're done writing it, for you to take a picture or scan it in, convert it to a PDF, and then upload it, you know, to the our Canvas page. If the upload, if you have any doubts at all about like whether the upload's working, just email me a copy, okay? And then we'll talk about the upload. But at least I'll have the time and date stamp that you did it within the window, and that, you know, you didn't take too long, or that you made the effort to actually try to pass it in. I mean, ultimately we want to get it so we can just hand everything in on our Canvas page, right? You don't want to be sending me all these emails, but if you have any doubts, like if you're not sure if it's actually there, just send me an email with the attachment on there. Does that answer your question about quizzes and availability and stuff?
Yeah, so would we have to like print out the quiz first, take the quiz, and then scan it back, or is it like putting it in a separate piece of paper and then scanning it back?
Yeah, it's a great question. So the things that you'll see online, like the quizzes and the tests and stuff, are not things that you're not gonna be writing on your computer screen. You're not gonna be inputting any answers into the computer, right? You can print out the quiz yourself and then actually work on that, and then scan it in, upload that, or you can look at the questions online and write them all down on a piece of paper. Okay, so make sure the piece of paper has your name at the top, right? So that I know, you know, when I look at it, like it's not just, you know, it's on your Canvas page or from your email, but it has your name on it too. And it has like, excuse me, the question number that you're working on. You don't have to, if you're just writing it down, you don't have to rewrite what the question is. But you definitely want to have the question number so I can follow along and grade it. So you don't have to print it out, although that can be helpful. So the printer isn't required, but definitely blank paper and a pencil and a calculator are going to be required. Calculator is, technically speaking, you can do the whole class without a calculator. We allow you to have calculators, and we, you know, I like them because they're allowed. I find them very helpful for graphing things to be able to get a visual. This is the one that we recommend is the Texas Instruments. Mine is an older model, TI-84 Silver Plus, plus Silver Edition. And then, you know, it's nice. We'll go through and we'll talk about like how we do certain things or what the graphs look like as we go along in the semester. So the calculator isn't, like I said, you can do everything without it. Technically, it'll make things easier for you. So we'll talk about like, you know, how you can use your calculator throughout the semester. Let's see, so that's our quiz. We have an exam, our midterm exam. We have only one midterm exam. It's scheduled right now for Thursday, October 22nd. So it'll cover all the material up until probably the Wednesday before. We'll spend that Wednesday actually, you know, talking about things and then like reviewing stuff. That exam is worth 25% of your grade. So we've like decreased how much the exam is worth because, you know, I've tried to increase the quizzes because we're going to have more of them. So it kind of gives you a chance to, you know, bring things together. Midterm will be cumulative up until that point. The final exam, which is 30% of your grade, the department, we all decided it's 30%. In years past, semesters past in person, it's been 40%, but we decreased it because we're remote and things are kind of crazy. We're trying to figure things out. The final will be 30%, and that will be cumulative for the whole semester. We'll talk about the final as we go, so just kind of keep that in mind. Midterm covers what we've covered up until that point, but the final is everything, okay? So it's everything that we've done at that point. So I don't know what the final exam schedule is going to be like yet. That comes from Northeastern, but as I know things, I will tell you, and I'll keep you in the loop on that. The final exam is something that all of the instructors, I think there are, geez, I think there may be like 10 or 12 of us as instructors for this course this semester, and we all contribute questions to the final exam. And so we'll talk about like what you guys can expect as we get closer to it. Don't sweat it. Let's see. Yeah, so on our syllabus, we've got some important dates. You know, when our classes begin, the days that we have holidays and stuff. I tried to delete those Zoom meetings so that we don't get confused, like, because we have some holidays on like Mondays and on a Wednesday and then Thanksgiving and stuff. If I've forgotten one, I'm sorry, it may be out there. Let's see, so as we go, right, this is our week 1, right? So we're actually going to jump right in today. We're going to start talking about chapter 1.1 out of our book. For those of you who've had calc before in high school, I know that the high school last semester, you know, your last spring kind of got all messed up. So we're kind of trying to take that into account in terms of like where you may be at with stuff. But this is the syllabus and the topics that are given to us by the department, and it's agreed on by the College of Engineering. So this is what I have no say in, like the topics that are being presented and how things, you know, are going to be what we need to cover for the class, because it's something that the university comes up with. Any other questions? I try to go through the syllabus, you know, talk about things. Like I said, if you guys can't access anything on the Canvas page, please let me know today. If you can't download the documents that are up there, like the homework questions and stuff, please email me and I'll send you a copy of it, and I'll try to track down why the Canvas page isn't working. And if you have access to it, that'd be great. Also, I wanted to mention, I don't know, I forget if I mentioned this in the assignment, in the announcement that I sent out before. You know, this isn't required, but I typed up the examples that I'm going to do in the class each lecture, right? So they're under lecture examples. This is example 1, example 2, so on and so forth. And that just makes it a little bit easier so that I don't have to write down the question as we're going along. It can save some time. Also, what I'm going to do is I'll work through the examples here on this paper, right? And then I can scan this in and then put them up online on our Canvas page so you can see the solutions for our lecture examples. It might be really helpful for you to print out these lecture examples before each class, and then you can take notes, right? Because I'm going to start doing notes on a piece of paper. And then when we get to the examples, you can write the examples here on this page. You don't have to, it's not required, but it can help you stay organized. And I'll tell you, I'm on example 1, or I'm on example 2, or whatever like that, so you can kind of get a feeling for it and follow along. But like I said, I'll scan these in by the end of the day and then upload them to our Canvas page so you have the solutions for our lecture examples. Okay. All righty. So seems like a lot to take in. We're going to be pretty flexible, you know, this semester, and kind of roll with things as much as we can, because we know this is a little bit extraordinary, and you know, appreciate your patience. If things aren't working or whatever, just let me know and email, and we'll see what we can do about fixing them. Okay. With that, let's go ahead and get started. And first, I also want to just jump in and say really quick that I know I talk fast, especially like when I get excited, I talk even faster. If you guys feel like I'm talking too fast, you can, you know, unmute your audio and say, can you just slow down, like slow your voice down a little bit, so that I'll know. Because to me, it sounds like I'm talking slow, but I'm well aware. People tell me I talk really fast. So I'll try to talk slower. Anyway, all right, so let's go ahead and get started. So this is, we're going to start with, all lined up. Okay, so this is chapter 1.1. Okay, and what we're going to talk about today in chapter 1.1 is what we call an average rate of change. We're going to start right from the ground. Okay, average rate of change, which we nickname AROC. Okay, so we're going to call it AROC as we go, so we can not have to say average rate of change each time. Okay, so let's come up with some definitions of what our average rate of change is. So let's write that. Okay, so our average rate of change, we want to be able to define it. So if you think about it, I've got a function, f of x, right? So my average rate of change is going to be change in my function, delta f of x, divided by the change in x. It looks like a slope, right? The change in y over the change in x, the rise over the run, which is exactly what this is. The average rate of change is the slope. We're going to talk about slope of what as we go along, okay? So delta f of x divided by delta x, right? More specifically, we're going to look at, this is going to be f of, I'm going to pick some point x1 minus f of x naught, right? All over x1 minus x naught, okay? Doesn't matter if this is f of x naught minus f of x1, as long as I have the order the same. So this is x1, this is x1, x naught over x naught. And also I need to specify too, it's a fraction, that x1 is not equal to x naught, right? That would be bad. We get a divide by 0 error there. Okay, so that's important. So our average rate of change, let's think about it. We're going to think about this. We're going to call this our slope of the secant line. And these words and these concepts, don't sweat it. I'm just throwing them out now, but we're going to spend time actually talking about exactly what this is. So the slope of the secant line. Just draw a graph here. So I've got my, oops, sorry, my function here. So this is f of x1, f of x naught. That's some value, right? So at x naught, my function had some value, right? And at x1, as I cruise along in my x-axis, right, and this is my y equals f of x, right? And at x1, right, I had some value here, okay? So as I go along, I'm looking at these values here, this one here had some value there. Okay, so now I've got this straight line between these 2 points here, okay? This is my secant line, right? Whatever f of x is, okay, I've got these 2 points that are on f of x, x naught and x1. And when I take that x value, x naught, and I plug it into my function, I get some value here. Do the same thing for x1, I get some value here. And I get this straight line. Okay, my function f of x is going to be doing something. I don't know what. We're going to talk about that as we go. Okay, but my secant line, right, is this straight line right here. Okay, so we'll just say f of x is our function of x. Okay, so as we go along, we're going to actually, we'll draw out our functions, we'll draw our secant lines so we can pick it up, okay? And if you guys, if I scroll off the page on this too, but you haven't finished writing it, you can tell me, oh wait, can you go back? And then I'll stop, okay? Sometimes in a classroom, it's easier for me to know. Yeah, obviously it's on a board, you know, I don't have to, I can leave it up on the board as I move on to other things, but I can't really see very well, obviously, if you guys are finished writing or not. So you'll want to tell me, give me some auditory feedback that you need time to finish writing what's happening. All right, let's just write as an example some things here. So if I write like velocity, we talk a lot about velocity in the class, so we'll talk about that really quick. So velocity, right, is our function of position, right? And it's like it's a function of position. So like it's our position over time, right? So velocity is a function of position. And then we talk about our average rate of change of position with respect to time, right? So where am I, at this, this position, at this time, at this position, at that time, I'm at that position. So I'm talking about like my change in position as a function of time gives you my velocity, okay? All right, so now this is like, I can write this out in terms of our delta f of x over delta x. In terms of our velocity, we would write it like this. This would be our position at time t naught minus our position at time t1, okay, divided by, now remember I have to keep these times in the same order, right? So this is time 0, time 1. Okay, so this is our velocity, right? Our position as a function of time minus our position as a function of a different time. I subtract these two times, making sure that the times are in the same order, okay? So we have to be really careful, right? Because I'm looking at my position at this time and my position at that time, okay? What I am not doing is I'm not taking an average of two velocities. Okay, so let's just make that really clear. So not average of two velocities at two different times. Okay, so we say it's an average rate of change, right? But we're not averaging our two velocities. I'm taking the average of my position, taking that difference. Okay, so that's really important because I'm not talking about the average of the velocities, but the average rate of change. Okay? Everybody have this before I change pages. Remember, I can't always see the chat. So if you guys are asking questions in the chat, I may not see them. So please feel free to ask me questions, okay, so that I can see that, I can hear you. All right, so let's talk about a definition. Okay, so definitions. So we're going to talk about real functions. This class here, and then calculus 2 also, when you take it next semester, deals with real functions only. Okay, there are a whole host of categories of functions that deal with the imaginary realm, but we in this class are dealing with only real functions. Okay, so we're talking about a real function. This is our function f, okay? And that's a function whose domain and codomain, which is also another way of saying range, are subsets of all real numbers, right? So this means all real numbers. Okay, so we're dealing with real functions in this class. Okay, so just kind of keep that in mind. All right, so another definition. So I've got two values, a and b. Okay, a and b are in the domain of f. F is our function, right? So they're possible inputs. They're potential inputs for our function f. Okay, and we want to also specify that a is less than b. Okay, so a is less than b. Both a and b are in our domain of f. We want to be able to say that the average rate of change, or our AROC, of our function, right, with respect to x. This is f of x, right? Our function of x, f of x. With respect to x, between, we're going to look at two different values, a and b, between when x is equal to a and x is equal to b. This is an a, sorry. When x is equal to a and x is equal to b, which gives us the interval along our domain, our x-axis, as going between a and b, right? So that was like kind of back to, right, I'm going to look at my interval from x0 to x1. Okay, this is my a, this is my b, say, for example. Right, so that's what we're saying here. I've got this interval. This isn't a coordinate, right? This is an interval of x values. is our interval. So the average rate of change, right, we're defining what our inputs are is, right, so I'm going to write this out like a slope, right? So delta y over delta x. It's always good to keep yourself remembering, right, our slope is the rise over the run, delta y over delta x, which is delta f of x all over delta x, okay, which I can write as f of b minus f of a all over, don't forget we have to keep these in the same order, b minus a. This here, and I'll put this in red here, this here, right, is called our difference quotient. Our difference quotient, okay? It's our slope, right? This is our definition of how we calculate slope. Remember, we said our average rate of change is the slope of our secant line. So this is what we're defining right here. I've got this function. It's doing stuff, right? I pick an x value, x equals a. I pick another x value, x equals b, right? And I figure out what's my function at a, what's my function at b, right? And I find out what's the slope. I connect those lines, okay? I connect those points into a line. That's my secant line, because secant means I have 2 points. Think about calculus, you think about the tangent line. We're going to get to that. We're starting off slow with just the secant line. Okay, so the secant line has 2 points along our f of x. Okay, and we're calculating what the slope is of that secant line. But we're using the average rate of change as our difference quotient. Okay, all right. It's a really important thing because we're going to use it a lot. Okay, so now let me just talk briefly about like our units. Right, so what are units? Because often we're talking about things like velocity and acceleration. But let's talk about our units here. So our units of our average rate of change are whatever our units are, units of our f, let's call it units of f of x, divided by units of x. Okay, so the units of your average rate of change are going to depend on the units of your function divided by the units of your x, of your inputs. Okay, and that's how we're going to figure that out. Okay. Any questions so far on what I've just covered? I'm going to go right into our example. I'm pulling out my lecture example page. And I'm going to go through example number 1, unless people have a question that they want to talk about here really quick before I do that. Okay. All right. So let's
Wait, I have a question.
Yeah, what's up?
Could you just quickly explain like the different units, like units of f of x versus units of x?
Yeah, sure. So say for example, right, if we have like the easiest ones to think about as an example are like velocity, right? So my velocity is going to be a slope, right? So if I have position over time, right? So my time is going to be my x-axis, my position is going to be my y, right? So it's going to be my f of x will be the position I'm at that particular time, right? So I'm at 30 meters at time 1, say for example, right? And I'm at 60 meters at time 2. So then my units for my velocity are going to be meters per second, right? And that's the slope of my secant line, okay? So because my units of my function are in meters, but the units of the input are in seconds, okay? So then when I check the slope of that secant line, or the slope of the tangent line, ultimately we're going to work towards, it's going to be in the units of my y over my units of my x, okay? So like we think about acceleration, right? That's meters per second squared, but it's really the velocity as a function of time. So it's meters per second per second. Okay, it's another way of thinking about acceleration. You can write the units for acceleration as meters per second or meters per second squared, right? So that's when we talk about units for our average rate of change. It's just whatever our units are, our function. Velocity, acceleration, those are the most common ones, right? Because we're science engineering majors, so we talk a lot about velocity and acceleration. But really, it can be anything. It can be like, dollars per hour. It could be, whatever rates you want to actually change that you want to measure. Okay. That help?
Yeah, I did.
Okay, and we'll go through, our questions. Our examples should help too as we go. All right. So example 1, my lecture example page, says, a car is moving in a direction designated as positive, okay, along a straight road. And at times t equals 0, 1, and 5 hours. We've got 3 different time periods. The car is moving at 30 miles an hour at, time t equals 0, 60 miles an hour at time t equals 1, and 40 miles an hour at time t equals 5 hours. Okay, so this is 30, 60, 40 miles per hour respectively, right? So 30 corresponds to time t equals 0, and so on and so forth. So what we want to know is, what are the average accelerations of the car on the intervals 0 to 1, 0 to 5, and 1 to 5. Okay, so this tells us these are our time intervals, right? So let's just write in, this is our time interval, okay, between these things here. And then we want to be able to figure out our acceleration. So our function, right, our y-axis is going to be in velocity, miles per hour, okay, and our time is going to be in hours. So the slope of that secant line is going to be miles per hour, miles per hour squared, which is our acceleration measure, just to kind of think about our units again. All right, so let's start writing these things down. So our acceleration, look at this. I'm going to try a different pen. You guys can tell me if these pens work better or not. So our change in velocity over our change in time. Okay, I like to kind of write things out. It helps me kind of keep track of stuff, which I write as delta V over delta T. Just I like to write out because it helps me put things in the right order when I'm going to put stuff down. So that means that my average acceleration is the AROC of velocity with respect to time. Okay. So my average velocity with respect to time. All right, so let's think about that. So my velocity equals v of t. Okay, so velocity is a function of time, is in miles per hour, mph, miles per hour, at time t hours. Whatever the time t is. We said 0, 1, and 5, right? We were given those times ahead of time. All right, so let's think about it. So our average acceleration is equal to delta v, over delta t. All right, so let's start plugging things in. We were told to look at different intervals, 0 to 1, 0 to 5, and 1 to 5. So we're just going to take them one step at a time. Okay, so the first one that we're going to do is this interval, 0 to 1. So this is our between times t equals 0 and t equals 1. This is when we started like measuring. At time t equals 0, what's happening? Okay, so now let's think about it. So velocity v of 0, right? My first one. What's my v of 0? We were given that, right? V of 0 had to be given something. Had to be given an equation where I could figure it out. Or had to be given actually what the values were. Okay, so my velocity at time t equals 0, we were given as 30 miles per hour. Okay, my velocity at time t equals 1, again, remember, we were given that at the beginning, is equal to 60 miles per hour. Okay, so I'm going to put these into here, right? Remember how we talked about that. So my average acceleration is equal to my velocity at time t equals 1 minus my velocity at time t equals 0, all over t1 minus time t0. And I'm going to put in t1 and t0 because maybe in this case it's 0 and 1, but in this case I've got like a 5 here. I don't want to like forget, and I want to make sure I can keep myself honest and write down the right numbers. So velocity at time t equals 1, we already wrote that as 60. Velocity at time t equals 0 is 30. Time t1 is 1 minus 0, right, is equal to 60 minus 30 divided by 1 is 30 miles per hour, which as an acceleration we can also write as 30 miles per hour squared. Okay. And that's our average acceleration between time t equals 0 hours and time t equals 1 hours. Okay. All right, so let's do that for the other ones too. I can see. Let me scroll up a little bit. So my next interval I want to take a look at is between 0 and 5. Okay, so this is between, let's write that down. So between time t equals 0, t equals 5. So let's actually, we're going to do the same type of thing that we did already. All right, so now I'm going to go my average acceleration as a function of time is, let's write it down first in terms of velocity at time, right? Velocity, 0, all over, okay? And I'm going to plug these in, right? Plug in these values. So we were given this right at the beginning, right? So that means I'm going to go, this is going to be 40 minus 30 all over 5 minus 0. Right, 40 minus 30 all over 5 minus 0. I can add and subtract. Right, 10 minus 5 is equal to 2 miles per hour squared. So that's my average acceleration between 0 and 5. Time t equals 0 to time t equals 5. Try our last time interval that we were given to look at. Scroll down a little bit. Okay, so 3, my last interval. 1 to 5. This we're going to go between time t equals 1 and t equals 5. This we're going to do the same thing. So my average acceleration equals velocity at 1 minus velocity at 5, right, all over t1 minus t5. I mixed it up a little bit, went smaller to bigger. It doesn't matter as long as I keep things consistent, you'll get the same answer. All right, so I'm going to plug things in. So time t equals 1, 60 minus 40, 1 minus, oops, sorry, 5 equals 20 all over, ooh, look, watch, minus 4. I have a negative number. Talk about what that means. So 20 divided by minus 4 gives you minus 5 miles per hour squared. So I have a negative acceleration. What does that mean if I have a negative acceleration? Does anybody know, like, what that means if we have a negative?
Means you're slowing down.
It means it's slowing down. It decelerated. So, you know, if I have a negative, you know, it doesn't necessarily mean you've done it wrong. So let's just write that. Okay, so this means, right, the negative, that our car decelerated. Slowed down, I'll write that, slowed down. Technically it decelerated. We kind of have to talk about speed versus velocity later. Okay, so we calculated our average rate of change, okay, for these different time intervals. This is for our acceleration, right? And we were given the velocity, right, at certain times, okay? So I was able to calculate what my average rate of change is for my acceleration, okay? Example 1. Anybody have questions on that before I move on to example 2? Okay, great, so I'm gonna turn the page. So example 2, example 2 says, what's the average rate of change in the area in inches squared of a widescreen 16:9 television screen? We're going to draw out a picture so we can kind of visualize what that means. With respect to the diagonal, like our diagonal, we're going to give the variable d, right? We're going to talk about if we go from d equals 32 to d equals 40. So this is our interval, okay, 32 to 40. And d equals, we're going to do another interval, d equals 40 to d equals 52. So I've got 2 intervals that I'm taking a look at, right? So there are a couple things that are happening here, right? I'm looking at the average rate of change of the area, right? So I've got this widescreen TV. It's a rectangle because it's 16:9, right? That's our ratio of our side lengths to each other, okay? And it's with respect to the diagonal, okay? So as I change that diagonal, how does the area change, okay? So as often happens in these problems, if you're not sure like where to begin with this stuff, start drawing a picture, right? Because drawing a picture is going to really help you figure out like how you need to think about how this is going to get pulled together. Okay? I always like to draw a lot of pictures. Like I graph the functions, or I'll draw like the geometry just so I can visualize. And it kind of gives my brain a chance to think about what I need to do on the back burner. Okay, so I'm going to start off by drawing a picture. So this is a rectangle 16:9. So I'm going to assume, you know, that it looks like this. Like most TVs, they don't have the, they're not like this, right? They're not turned on this angle. They're like a rectangle, like in this direction. Okay, so that means that my ratio is 16x by 9x. X is, you know, I suppose I could have a 16-inch by 9-inch TV, or maybe I want to scale it, but this is like, as I scale it up, it still maintains that same ratio of 16 in the width by 9 in the height, okay? Which means also that because we're talking about the diagonal, I'm going to draw my diagonal this way. And it's a rectangle, so I'm just going to remind myself that rectangles have right angles on the sides, which is really nice because that means I can use the Pythagorean Theorem. I love the Pythagorean Theorem. right, so let's write down. So I've got a picture, right? And so by drawing the picture, it starts to help jog my memory of how I can come up with like an equation that's going to relate the sides to the diagonal, right? If I'm just trying to think about it on the fly without a picture, it may take me a little longer, especially if I'm stressed out because I'm taking a test and it's time and I need to do it. So pictures always help you. So let's write down what we need to do. We're going to use the Pythagorean Theorem. All right, so that means, right, I'm going to go like this. And watch out. 9x squared is quantity squared. 16x quantity squared equals the diagonal squared. Okay, so I'm going to square things up. I'm going to square this, add them, right? Because I'm going to get 81x squared, plus 256x squared equals d squared. I'm going to sum them up together. I'm going to get 337x squared equals d squared. Okay, now this is my first equation here, but I want this in terms of d. I don't know what x is, so what I'm going to do is I'm going to solve this in terms of x squared. So I'm going to say x squared equals d squared all over 337. Right, I'll leave it like that. That's my first equation. But the problem said I need to focus on the area. How does the rate of change of the area change? Well, this doesn't tell me anything about the area, right? So I need to remember, going back to my geometry days, right? I need to remember what's the formula for an area of a rectangle. And oops, I can spell. Rectangle is base times height, right? So I'm going to write that down. So I'm going to go area equals 9x. I did this height times base. Times 16x, right? So now I'm going to get my area. That's going to be 144x squared is my area. Again, right, I've got this x squared equals area. So I'm going to solve this in terms of area. So let's write that down, right? So I'm going to say this is going to be x squared, right, is going to equal to area all over 144. Now look what I did. I have two equations and one unknown. So I have this solved for x squared, this solved for x squared. I can set them equal to each other. And now voila, I have an equation that relates area to d, okay, which is what I wanted to do all along. This is a lot of setup. We haven't even gotten to the calculus part yet. So let's go ahead and write that out. So I can write d squared all over 337 equals area all over 144, which means because we were asking about area as a function of d, so I'm going to rewrite this as area equals, so this is going to be area, this is in inches squared, equals 144 all over 337 d squared. Okay, so now I have a function. I had to derive that myself. Like in other examples, we'll give you the function and you'll be asked to do stuff, but in this case, we had to actually come up with it ourselves. So this is the step, right? So it helps to draw out a picture because then I can relate the sides to the diagonal. But I'm asked about the area, so then I can remember, right, what's the area of the rectangle, and then I can figure out an equation that's going to relate the area to the diagonal, which is what I want. Now I can start thinking about the area as a function of diagonal. I can start thinking about my average rate of change. So now we're going to get into the calculus part of it. Okay, so up a little bit. So I'm going to do the AROC of area as a function of our diagonal. Okay, we have a couple intervals that we were talking about, right? The first interval that we wanted to do was I'm going to go from my diagonal equals 32 inches to my diagonal equals 40 inches. This is our first set of intervals that we want to talk about. This is our interval. I'll write that down, interval of d values. Okay, because this is area as a function of d, so d is our input and area is our output, right? So it's going to help us. So I'm going to go my area as a function, my average rate of change of my area as a function of the diagonal is equal to, right? I'm going to say the area when the diagonal equals 40 minus the area when the diagonal equals 32 all over. Remember to keep these the same order. Okay, so I can plug them in. So that means I have to be careful, be very careful about your, I've got this 144 over 337 in both of these here. So I can actually factor that out. So I save myself the hassle of maybe making a mistake. So this is, I'm going to plug this in. So this is going to be 144 all over 337. I factored this out because I have it here and here. So I factored it out. So I'm only multiplying once. It's just how I like to look at it. Okay, so what I'm going to do is now, this is 40 squared. This is my d squared minus 32 squared all over 40 minus 32. So watch your order of operations, square it, subtract, divide by this difference, right? And then multiply by this fraction here. And what I get, it's going to be approximately 30.7656. Now watch our units, right? So this is inches squared per inch. Okay, so let me write this down. This is the average rate of change. Average rate of change of area, which is inches squared, per change in diagonal, which is in inches. So be really super careful that you don't go, oh, inches squared divided by inch, I'm going to cancel it out and just get inch. Okay, that would be wrong, because what we're doing is we're figuring out what's the average rate of change of our area, inches squared, as our diagonal is changing, right, from 32 inches to 40 inches, right? So our area is changing at 30.7, 30.8 inches squared per inch. It's going to grow, right? It's going to grow at this rate right here, okay? Be really careful. Don't get clever, right? And then cancel out these units, leave them as they are. Okay, so let's try the other. So as we go from the diagonal equals 40 inches to the diagonal equals 52, let's check the average rate of change, okay? Let's see, you know, does the average rate of change get bigger or smaller? Does it, you know, how does it change as we go? So this is our diagonal. Okay, so now I'm going to take a look at my average rate of change of my area as a function of the diagonal. Okay, and I'm going to go my area at 52 when the diagonal equals 52 inches minus the area when the diagonal equals 40 inches divided by, right, when the diagonal equals 52 minus the diagonal equals 40. This is our slope, right? So we're going to plug this in. Again, I'm going to factor out my 144 over 337. You don't have to. Okay. Don't forget to multiply it in the end. So now I've got 52 squared, that's my d squared, 52 d squared, okay, minus 40 squared all over 52 minus 40, okay? Watch your order of operations. Again, square, subtract, divide, multiply, okay? So now when I do this, right, I get this is approximately equal to 39.3116 inches squared per inch, okay? So the area, average rate of change of our area, right? It's not just that the area is going to be bigger when we change the diagonal, but the rate of change as I go from a smaller diagonal to a medium-sized diagonal, right? As I is smaller, 30, then when I go from medium-sized to larger, so the area, the rate of change of the area is getting bigger, much faster, right? As our diagonal gets really big. You can see some of these, like, you know, flat screen TVs, some of them are really ginormous, right? The diagonal is pretty big, but, you know, if you keep the aspect ratio the same, okay, the area is going to be pretty big, okay? Anybody have questions on this before I go into the next example?
Yeah, I have a question. Could you, like, just quickly go over, like, how you came about the 144 over
337, sure. So let's go back to a different color here. So we, at the beginning, we were told, right? So let's go right back to the very beginning. So it comes back to the geometry. So I've got this, the TV is a rectangle. Most of the TVs now are rectangles, but we're told here it's going to be a rectangle with the ratio, with the height ratio of 16 to 9, right? So that it's a rectangle. You don't even know what X is. X could be 1, X could be 10, right? I mean, it's, you know, I have to keep the aspect ratio the same, right? So 16 along the width and 9 along the height. And then it's a rectangle, so I've got a diagonal, because what we're trying to do is we've got a diagonal, like, right? TVs are always talked about in terms of diagonal. We want to know, like, what's the area of this TV, right? And then we want to know what's the rate of change of that area, right, as the diagonal gets bigger, okay? But the aspect ratio stays the same, okay? So I went and I drew a rectangle, right? I like the pictures. So I said 16x by 9x, right? X is just my, you know, multiplication factor. My D is my diagonal. It's a rectangle, so it's a right angle. I need to have an equation that's going to relate my sides to my diagonal. Pythagorean Theorem helps me with that, right? So a squared plus b squared equals c squared. I got these from here. So I've got this x squared. I don't know what x is, right? I know what d is, right? That's my diagonal that I'm working towards, but I don't know what x is. So I'm just going to solve for x. It's my unknown for now. So I need another equation because they're asking me about area, right? Area as a function of diagonal. Well, all I have right here are sides as a function of diagonal. And if I calculate out the geometry, the area of the rectangle, it's, you know, base times height, right? Well, that just gives me the area in terms of the sides, right? 9x by 16x, which gives me 144x squared. But look, I've got x squared here and x squared there. So that helps me relate. I can set these two equal to each other. I'm going to set these two equal to each other. So I get d squared over 337 equals area over 144. Right? D squared over 337 equals area over 144. Well, I was told at the beginning of the question, area is a function of diagonal. So that means I'm going to solve for the area here. So this is area. You can even write area as a function of the diagonal, area of D, right? So 144 over 337 times D squared. See how I got that part?
Yeah, I think what initially confused me was the 144x to area over 144.
144 x squared equals area. So 9 times 16, right? So I just multiplied these out. So I just took the area of the rectangle, base times height. 9x times 16x is going to give me 144x squared. That's my area. I don't know what x is, but I don't know what x is there either, but it's the same x. Let's set those x's equal to each other. So now I can equate the area with the diagonal. I have some kind of a factor that will allow me, like this 144 over 337 is related to the 16 by 9 aspect ratio that we're trying to preserve, but it relates the area to the diagonal. It's the diagonal squared, right? So once we have an equation that relates the area to the diagonal with this scale factor, the scale factor comes from our 16 by 9 ratio, right? Then I can start doing the average rate of change of area as a function of the diagonal length. But I had to derive it myself because I wasn't given it. Not like I'm given a function of x and I'm asked to find stuff. I had to come up with this equation myself. Does that help?
Yeah, it does. Thank you.
Okay. Good. Right. So let's do. Let's move on a little bit so we can move on. The class. I know the Zoom lessons. The Zoom only let me schedule things for the quarter hour, but I'd like to keep them on schedule because I don't know about you guys, but I have 3 classes back to back in the morning. So my next class starts at 9:15. So I need to make sure that I stay on schedule. I'm sure you guys all have classes like that too. So let's keep talking about. So I'm going to talk about our secant line, right? And then what we need to do. So we're going to talk about things. We'll do it with a function first, an example, and then we'll start kind of deriving concepts of stuff. So example 3 is a function that we're going to use to help us explain what we're trying to do with the secant line. So example 3 says, given the function y equals f of x equals 4 minus x squared. So we're talking about a parabola. We'll graph that out in just a second. What's the average rate of change of y, or f of x, with respect to x on the interval 1 to 2 and on the interval 1 to 1.5? Okay. Now, like I say, I like to plot these out. So, I mean, it's a parabola, so we should be able to do it fairly easily. But let's just go ahead and take a look. So I'm going to go, 4 minus x squared, right? And then I'm going to graph it out. This is what it looks like. So they want me to look at along the interval from 1 to 2 and from 1 to 1.5. So I could zoom in even a little bit, but let's draw this, function down here. So I'm going to draw this out. 1, 2, 3, 4. There's our y-intercept. 1, 2. Right? And then it, goes down this way. I'm not going to worry about drawing the rest of it because we're focusing here along this interval 1 to 2 and then 1 to 1.5. Okay, so I'm looking at what are my values here? What are my values there? What are my values here, right? And we're going to come up with equations that pass through these lines, these points here. Okay. All right, so let's go ahead and start working on that. So on our first interval, I'm going to take a look at 1 to 2 as an interval. Okay, so we're going to look at delta y over delta x. So I've got this function, right? And I want to be able to come up with, from 1 to 2, right, what's my, I'm going to go from 1 to 2. What's my line? I didn't draw that very straight. It should be a straight line, but in red here. That's what we're working on here. I'll do a different color for the other interval. Okay, so that's what we're looking at. What's the slope along that? So I'm going to go f of 2 minus f of 1 all over 2 minus 1. Okay, so now I've got this function. I can plug in when x equals 2, what's my value? When x equals 1, what's my value? And I've got these values for x. So I'm going to plug these in, right? I'll just do it all out so you can see. Remember, this is your function. I'm going to plug these all in. So 4 minus 2 squared minus 4 minus 1 squared, right, all over 2 minus 1. I'm plugging them into my function f of x. Okay, that's right. I'm not pulling it out of thin air. It's coming from our function that we were given. So that's going to give us 0 minus 3 all over 1, which is equal to minus 3. And it makes sense. This right here, this is the slope of this line right here. So I'm going to write down slope equals minus 3, right? And it makes sense, right? You can see it's a downward pointing straight line. It has a negative slope. So those things should line up with each other. Slope equals negative minus 3. All right, let's take a look on the other interval. This one, we're going to go from 1 to 1.5, right? So this here, 1.5 right there. Sorry, can you see that right there? So I'm going to draw a line from here to here. I'm going to try to exaggerate these. Oops, it should be straight up like that. So we want to look at what's that slope equal to. That's what we're going to calculate here. Okay. So from 1 to 1.5, I'm going to go delta y over delta x. What's the slope of that line? So this is f of 1.5 minus f of 1 all over 1.5 minus 1. So I'm going to plug this into my function, 1.5. So it's going to look like 4 minus 1.5 squared minus 4 minus 1 squared all over 1.5 minus 1. Right. So I plug, this is my x. I'm plugging that into my function here that we were given. So I'm going to plug that in, and I'm going to get 1.75 minus 3 over 0.5, which is equal to minus 2.5. Okay, so let's put that in a different color. That's our slope. Slope equals minus 0.5. And it's negative, sorry, I can't say that. It's negative also, which makes sense because it's a downward pointing straight line. Okay, so what we've done here is we've got this function, f of x equals 4 minus x squared. It's our parabola, right? I've got what we call secant line. Secant line intersects our function in 2 places, 1 and 2. X equals 1, x equals 2. I've got this red line. Okay, I'm coming up with the slope of that line is the slope of our secant line. We're going to use the whole concept of a secant line to help us build up the tangent line. So bear with me here if it all seems really rudimentary. Why am I talking about this? Right? And as I change, right, my x values, right? So I moved my x from 1 to 2. I moved it from 1 to 1.5. I narrowed that range a little bit. Okay, so my secant line slope is going to change, right? This is the green line here. Okay, that's going to change as well. Okay, so now let's talk about, you guys, first off, I'll see how we did this stuff. I need to kind of wrap this up quickly here. Okay, so let's talk about like what we were trying to do here. So this is our definition of a secant line. Oh, sorry, my phone's ringing. I gotta turn off this. All right, so okay, so we've got a secant line. This is important. It seems really rudimentary, but it's important because we're going to use it to build up the concept of a tangent line. Okay, so we've got some function, given a function of x and 2 x values. We'll call them a and b. These are on the domain of f, okay? On domain of f, okay? The secant line secant line of f for x equals a and x equals b. This is like when we said x equals 1 and x equals 1.5, or x equals 1 and x equals 2, right? That's 1, that's 1.5, for example, right? That secant line has 2 points. Those 2 points are this: a, f of a, and b, f of b. Okay, that's what defines a secant line, 2 points. Okay, our tangent line, which we'll talk about later, has only 1 point. Okay, but we're going to use the concept of the secant line to help us derive what the tangent line is. Okay, but first remember, secant line has 2 points. Okay, we choose what those points are. Okay, and we can come up with, we're going to have to talk about the equation of the secant line. Okay, you'll be asked to come up with the equation of the secant line or the equation of the tangent line. Okay, it's always easier if you do things in the point slope form, because you can actually get a point on the when we do these things here. We have a point on the line. I've got this here. That's my x value. I've got my f of x. Okay, so that's going to give me points on that line. So let's draw this again. This is from our example. I'll put this down here. Of secant line. I just want to talk about the equation of the secant line. If I go from my interval from 1 to 2, this is my interval, right? So I'm looking at what's the particular value here. So I've got x equals 1. This point here is 1, 3. Okay, and it has a slope of -3. This point 1, 3 is common in both, so I'm going to use it for both of those. So I'm going to say my equation of my secant line is going to be y minus 3 equals -3, x minus 1. Remember your point slope form, right? It's y minus whatever the y point is. So let's just write that down. This is going to be y minus y naught equals m, my slope, x minus x naught. That's your point slope form. It's the easiest form of the line. You don't have to calculate y equals mx plus b. You already have the m. That was your average rate of change. That's your slope of your secant line. But the point on the line, you already have it here. Point slope form is your easiest. When we go from interval 1 to 1.5, right, this point here, 1, 3, is on that line as well. So I'm going to use that again. So I'm going to go y minus 3 equals minus 2.5. See how the slope changes. X minus 1. Okay, so that's the slope of the secant line going from x equals 1 to x equals 1.5. This is our equation of the secant line going from x equals 1 to x equals 2. Right? They pass through the same point, but they have different slopes. Okay. We're gonna this is the end of the lecture today. Okay. Sorry, I went over a little bit. I won't do that again. And then if you want, I can fill out the last the last example, or we can do the next example tomorrow at the beginning of class to talk about, kind of fill out what the rest of the lecture examples are. But you will be asked to do things like the equation of the tangent line or the equation of the secant line. So keep that in mind. If you guys want to go ahead and take a look at the homework, they should be posted on our Canvas page. You should be able to download them. If you can't, let me know, and I will send them to you so you can get those and download those. And feel free to ask me questions tomorrow in class about homework problems that you did this afternoon. And then we can go over some of those problems. Okay. All right. Anyway, you guys, have a great day. It was nice meeting you, sort of. Bear with me here as we're trying to do this class remotely, and we'll figure it out. Anyway, have a great day. And if you guys have any other questions or you didn't want to ask today, you're free to come to office hours at 1 o'clock. That's the link in the syllabus. Tells you the office hour link with the password. And then I can be free to answer any other questions in more detail then. Okay? Have a great day, guys.
Thank you.
Thank you, Prof.
Bye.
Thank you.
Thank you. Bye.
Hey, guys.
Thank you. Bye.
Bye.